Hey everyone, and welcome. Today in this explainer, we're diving straight into the fascinating mathematics behind a surprisingly short Python simulation script. We're going to explore exactly how we can calculate the true age of a mineral just by algorithmically processing its trapped electron counts. It's basically a time machine built out of math. So think about it. How do we actually code the age of an artifact? I mean, translating thousands of years of physical, geological history into a strict mathematical model? That takes some incredibly precise logic. Let's break down the underlying math of this script, line by literal line. All right, here's our quick roadmap for the explainer. We'll start with the artifact aging simulation, then move into decoding crystal efficiency math, look at the quartz sample data, and finally we'll wrap up with executing the function. Let's get right into it. Section 1, the artifact aging simulation. Okay, looking right at the top of the script, we see import random. Now, in our mathematical model, this is absolutely crucial. It introduces necessary statistical variability. Think of it like applying a Gaussian distribution to our final calculation, which perfectly represents the natural, unpredictable fluctuations of background radiation over thousands of years. And right below that, we define our core engine, the simulate_artifact age function. The docstring for this code lays its purpose out perfectly. It simulates the aging of a mineral based on trapped electron accumulation. Physically speaking, minerals absorb background radiation, which literally traps electrons right there inside their crystal lattice. Our function takes this physical count and translates it into a temporal age. How? Well, ultimately, it divides the total true electron accumulation by an expected annual radiation dose rate. It's just brilliant. Section 2, decoding crystal efficiency math. Inside our function definition, we've got two primary variables to look at. First up is total_trapped electrons. This is our raw input, literally the absolute number of electrons our virtual scanner detects. Then we have crystal efficiency, which acts as our constant modifier. You see, the raw total alone isn't our final dividend. To calculate the true total radiation exposure before we can even try to find the artifact's age, that raw total has to be mathematically divided by this efficiency modifier. And take a look at this 0.05 efficiency parameter. In the math world, this translates to a strict 5% constraint. What that means mathematically is that the trapped electrons we actually see represent only 1/20th of the total radiation the mineral originally absorbed. So, to find the true exposure, our math is going to have to either multiply the raw count by 20 or, equivalently, divide it directly by 0.05. Section 3, the quartz sample data. At this point, the code actually transitions from just setting up the theoretical math to executing the simulation. It's guided by a very specific comment in the script that reads, "Let's assume our virtual scanner detected." So we're stepping out of the abstract theory now and jumping into a fully hypothetical scenario with a specific target quartz sample. 450,000 trapped electrons. Wow, that is our primary integer. Every single one of those trapped electrons is a microscopic physical event captured deep within the quartz, and together they provide the exact numerical input we need to fire up our algorithmic engine. Section 4, executing the function. Okay, let's walk through the actual detailed math here. Step 1, the system detects those 450,000 electrons. Step 2, it applies our 0.05 efficiency constraint. So we divide 450,000 by 0.05, which gives us a massive true total exposure of 9 million electrons. Then, step 3, we simulate the age. If we assume a standard background radiation rate of, let's say, 300 electrons per year, we divide our 9 million by 300. That gives us a solid base age of 30,000 years. From there, the random module steps in, applying a standard deviation to output our final simulated result. Let's look exactly at how the code commands this execution. The very last lines of our script do three highly precise things. First, it creates a new variable named sample_measurement. Second, it assigns our measured integer value of 450,000 directly to it. And third, it takes that fully loaded variable and passes it straight into our simulate artifact age function. So think about what's happening here. On one hand, we have a completely static count of 450,000. But on the other, the moment we pass it into simulate artifact age, it completely transforms into a dynamic operation. That single integer drives a complex equation that systematically divides out the physical inefficiency and the background rates, ultimately yielding a real-world timeline.
So with a base age of 30,000 years and our random module applying a realistic 5% margin of error, our quartz mathematically computes to an age between 28,500 and 31,500 years old. Pretty amazing, right? But this actually raises a much deeper question for our code. If crystal efficiency naturally degrades over long periods of time, how would you rewrite this exact algorithm to account for a dynamic decaying efficiency rate rather than just a constant? I highly encourage you to go adapt the script, run the math, and find out.